In this section, we will look at the normal distribution, which is a statistics topic that you will study further in Year 2 Maths. We will look at how to construct a confidence interval for the mean of the population based on a sample. Some continuous random variables can be modelled using a normal distribution. The graph of a population that is normally distributed has a bell-shaped curve. This graph is symmetrical about the mean mu. So the population mean is in the middle and splits the curve in two. This means that approximately 50% of the population lies above the mean and 50% lies below the mean. An example of this might be heights of people. The population mean of a normal distribution is the same as the median and the mode. They all lie along this central line. Similar to histograms, the area under the curve is used to calculate the probability. The spread of a population is measured by its standard deviation sigma. Remember that the standard deviation is the square root of the variance. If a random variable has a normal distribution, we will write it like this. X has a normal distribution with a mean mu and a variance sigma squared. Notice it's the variance that is given here, so if you wanted the standard deviation, you would need to take the square root. It can be calculated that approximately 68% of the population lies within one standard deviation above or below the mean. So this is approximately 34% on either side. Therefore, if we mark mu minus sigma and mu plus sigma on the curve, we can see that there is 68% of the population between those two values. Similarly, if we go two standard deviations either side of the mean, so between mu minus 2 sigma and mu plus 2 sigma, we expect to see about 95% of the population lying between those values and only 5% lying outside. If we go 3 standard deviations each side of the mean, the vast majority of the population, 99.7%, is now lying within that range. So to lie more than 3 standard deviations away from the mean, a data point would be a real outlier. This data shows the weights in kilograms of 225 dogs. We can assume that this data follows a normal distribution. So if it was plotted, we would get a bell curve like we saw on the previous slide. Pause the slide now and randomly choose 6 of these dogs and then find the mean of that sample. Add your 6 values together and then divide by 6. Press play when you have done this. Now that you have your mean of the sample of 6 dogs, how confident are you that the mean of the population, so the mean of all 225 dogs here, will be the same as your sample? Well, the chances of your sample having the exact same mean as the population is very unlikely, but it should give you quite a close approximation. It should be a good estimate of the population mean. How confident are you that the mean of the population is within plus or minus 5 of the mean that you found? So if you took your sample mean, added and subtracted 5, how confident are you that the population's mean will be between those two values? You'd probably find that you were quite confident in this statement. Now pause the slide again, and this time take a random sample of 12 dogs from the data. Find the mean of these 12 weights by adding them up and dividing by 12. You should have got a slightly different sample mean this time. Is this sample mean a better or worse approximation of the population mean compared to the sample of 6 that you initially took? You'd expect that this larger sample would give you a better approximation. A confidence interval is a region bounded by two numbers, so that you can say you are a certain level of confidence that the population mean lies between those values. For example, for a 90% confidence interval, you'd give two values and say, I'm 90% confident that the population mean lies between these two values. If you take a sample and find its mean, that is denoted by x bar. We could construct a normal distribution symmetric about this number, x bar. And if we wanted to be 90% confident that the mean of the parent population, so the mean of all of the values, is between two values a and b, we would need to construct a confidence interval. So mu is the population mean, and we are 90% confident that mu lies between a and b based on our value of x bar. This is a symmetric confidence interval because a and b are the same distance away from x bar. Confidence intervals are written in brackets with a comma between. The standard normal distribution is denoted by the letter capital Z. Z has been standardised so that the mean is 0 and the standard deviation is 1. So if we were to draw a bell curve to show this, we would see a mean of 0 in the middle, and we would see 1, 2, 3 standard deviations either way. Remember that 99.7% of the data lies within 3 standard deviations. So for this curve, it would lie between -3 and +3. A z-score tells you how many standard deviations a value is from the mean. So for example, a z-score of 2.1 would tell you that you were 2.1 standard deviations above the mean. A z-score of -0.6 would tell you that you were -0.6 standard deviations below the mean. To find a z-score, we can use the inverse normal function on the calculator. This is found on menu 7, which is the distribution menu. You would go to inverse normal, and you would need to put in the value that would get you a 90% confidence interval. Now the calculator works out the probability of Z being less than or equal to a particular score. So if we want to know what Z value to use for this confidence interval, we would need to consider the whole area to the left of this point. So this includes the 90% in the middle of the confidence interval, and also the 5% at this end. The only part it wouldn't include will be the 5% at the other end. So we actually need to look up 90%, or 0.95. This would give us the Z value here. Notice that because it's a symmetric confidence interval, the Z value for this side will just be the negative value of that. So if we put 0.95 into the inverse normal function on the calculator, you need to make sure that sigma is set to 1 and mu is set to 0. The value that we get for the z-score for a 90% confidence interval will be 1.64. So every 90% confidence interval will use 1.64 for z. Other confidence intervals with different percentages will have different z-scores calculated in the same way. We know that the size of a sample has a big effect on the confidence interval. If your sample had a size of 10, then your 95% confidence interval may look like this. We are 95% confident that the mean mu of the population lies between A and B. If we had taken a larger sample of 20, we would assume that the sample mean for this sample is a better approximation and therefore more accurate for working out the mean of the population. So therefore, the confidence interval that we would get would be narrower. A and B would be closer together. We are still 95% confident that mu now lies between these two values A and B, which are closer. If we had taken a sample of size 50, which is much larger, we would get a very narrow confidence interval because we would be 95% confident now that the population mean lied between these two values that are quite close together. So as the sample size increases, the confidence intervals become smaller. We can take this into account using the standard error. The standard error is the standard distribution for the sample divided by the square root of the sample size. You can see here that the standard error depends on the spread of the initial population, which is sigma, and the size of the sample, which is n. As n increases, the standard error becomes smaller, as we have seen above. If we have a population with a normal distribution and we know the variance of that population already, we can use this formula to calculate a symmetric confidence interval. This is calculated by finding the sample mean x bar and the z value for the particular confidence interval we are looking for. We then calculate x bar minus z multiplied by the standard error and x bar plus z multiplied by the standard error. This gives us the two values for the limits of our confidence interval. Going back to the data with the masses of the dogs, we are going to take a random sample of 12 dogs. We are going to use the standard deviation of the population as 5.14. This has been given in the question. And using this, we will construct a 90% confidence interval. So first we take a random sample. This could be calculated using a random number generator on a calculator. We then add these together and divide by 12. This gives us a sample mean of 21.74. As previously seen, the Z value for a 90% confidence interval will be 1.64. We were told in the question that the standard deviation was 5.14, and we are going to use n equals 12 because that is the size of our sample. Using these four values, we can now put them into the confidence interval formula to find the confidence interval. Substituting these values in gives us a lower limit of 19.3 and an upper limit of 24.2. This means that we can say with 90% confidence that the population of the mean weight of all of the dogs in the population is between 19.3 and 24.2. The actual population mean, when calculated from the 225 dogs, is 20 kilograms. So we can see that this seems to line up with the confidence interval that we have found. We're now going to consider the volume of milk in a standard glass, which is assumed to be normally distributed with a standard deviation of 4.1. A sample of 12 glasses of milk were taken and measured, and the volume in each one was recorded. We're now going to construct a 95% confidence interval for the mean volume of milk in a standard glass. First of all, we need to calculate x bar, the mean of the sample. This involves adding up the 12 values in the sample and dividing by 12. Here we have 151.5. We now need to calculate the z-score for a 95% confidence interval. So for a 95% confidence interval, we actually need to substitute in 97 0.5%. This is best illustrated with a diagram. Here's the bell curve. To be 95% confident, we would have an area of 95% or 0.95 in the middle. This leaves 5% left over, and as it's symmetrical, this means 2.5% on either side. If we want to find the Z value here, bearing in mind that there would be a negative Z value at the other side, but to find the positive Z value, we need to consider all of the area to the left of this point. This includes the 95% here and the 2.5% here, which leads us to 97.5. This means that we are going to look up 0.975 in the inverse normal part of the calculator. Remembering to substitute in the mean is 0 and the standard deviation is 1, we find that Z is 1.96. We can also calculate the standard error, remembering that the formula for standard error is sigma over root n. So for this example, it will be 4.1 over root 12. You can either leave this for now as 4.1 over root 12, or you can calculate it to a sufficient number of decimal places, 1.184. We can now substitute the values we have into the confidence interval formula. This leads us to a confidence interval of 149.2, 153.8. So we can say with 95% confidence that the mean volume of milk in a standard glass lies between those two values. In the context of this question, we can write this statement. If a population has a normal distribution, but the variance of that population is unknown, we can estimate it from the sample using an unbiased estimator. In order for this to work, the size of the sample needs to be sufficiently large, and we tend to define this as n is greater than or equal to 30. Variance of a set of numbers can be calculated using this formula, sigma x squared over n minus x bar squared. This could also be calculated using the sigma squared button on a calculator. This is called a biased estimator for the population variance. This is because samples and populations tend to be slightly different in terms of their spread. So if we were to use the variance of the sample to try to estimate the variance of the whole population, it will be slightly biased. Populations tend to have a slightly larger standard deviation and variance than a sample. If we want to find an unbiased estimator, we need to do a calculation with this variance of the sample. This calculation involves taking the biased variance, the variance of the sample, and multiplying by n over n minus 1, where n is the size of the sample. For example, if the size of the sample was 30, we would multiply by 30 over 29. This means the unbiased variance is always slightly larger than the biased variance. Alternatively, if we had the original set of data, we could put this into the calculator, into the statistics function, and there is an s squared function on that calculator which we could just use. However, in some questions we are not given the original set of data, and instead we are given these values, sigma x and sigma x squared. We would use these to calculate the biased variance and hence the unbiased variance. So it depends on what you were given in the question, either the full set of data or the statistics, in order to decide which formula you were going to use. The sample mean can just be used as an unbiased estimator for the population mean. We don't need to do anything to x bar in order to use it to estimate mu. When you put data into your calculator, it will give you both values. It will give you the variance using the sigma function, sigma squared function, and the unbiased estimator using the s squared function. the population has a normal distribution and the variance is unknown, then the formula for the confidence interval becomes this. It's the same as the formula for when we know the variance of the population, except instead of using sigma, the standard deviation, which will be given in the question, we have to calculate S, an unbiased estimator, first, and then substitute that in. So in this case, X bar is the mean of the sample, Z is the Z-score for the confidence interval you want to find, S is the unbiased standard deviation, and N is the size of the sample, and in order to use this, N would need to be greater than or equal to 30. In this example, we are told the height of workers in a factory are known to have a normal distribution, and a random sample of 35 workers has been selected. We are not given the original set of data here, however we are given these summary statistics. We are told sigma x, the sum of all of the heights of the 35 workers, is 62.3, and we are told the sum of the heights squared is 111.1. We're going to use these summary statistics to construct a 99% confidence interval for the mean height of all of the workers. So first of all, we calculate X bar. Even though we don't have the full set of data, we do know the sum of all the X values is 62.3 and that there are 35 workers. So we can calculate X bar using 62.3 over 35. This gives us 178 as X bar, 1.78 as X bar. S squared, we can use the formula here. So we have sigma x squared over n minus X bar squared. X bar is the value we found here, so that's there. The thing in the brackets would give us a biased variance for the sample. To find an unbiased estimator for the population variance, we would then multiply by n over n minus 1, so 35 over 34. Remember that this is S squared, and the formula that we will need will just be S, so we will need to square root this answer when we substitute it in. We're now going to calculate the Z-score for a 99% confidence interval. So for a 99% confidence interval, again, a diagram can help just to clarify what's going on here. We have 99% as the area between the two values. We then have 1% left over, which will be 0.5% on each side. And the Z-score is found by considering the area to the left of this point, which is 99.5. So we would substitute 99.5% or 0.995 into the inverse normal function of the calculator. This leads us to 2.576 for Z. We now calculate the standard error. Remember, the standard error for this would be S over root n. So in this case, it would be our S value divided by the square root of 35. We then substitute into the confidence interval formula. This gives us a 99% confidence interval for the heights of the workers as 1.75 to 1.81. We can say with 99% confidence that the heights of the workers, the mean height of all the workers, is between these two values. Now complete exercise 6A on page 119.